Okay, so thank you all for making it. I know it's hard to come after work and just learn about more programming. Real quick, I'd like to say thanks to Jillian for organizing this whole event. She's in the back, so let's give her a round of applause. And thanks to the speakers, because I'm really excited about what everyone's going to talk about. Uh, so I was told that I had to do some jokes, so I don't really know jokes. But I have one Haskell joke, but you probably wouldn't get it until later. Okay, so our first talk is going to be our Prismatic's own Logan.
Hi guys, thanks for coming out. Didn't realize so many people love functional programming. So my name is Logan Linn, and I'm going to talk about single direction data flows with ClojureScript. I think I changed the name of this talk about 5 minutes ago, so I can give you a new one in about 5 minutes too. So just a little bit of background, I work at Prismatic, and here we build personalized interest-based news feeds. So what we do is we collect our users tell us their interests, whether it be like programming, Clojure, functional programming, specific things like Haskell or Clojure. And then we crawl the web and build feeds of interesting content for that. So this involves a lot of machine learning to classify content that we find on the web, some machine learning for relevance, and then building all of these clients to display this rich content. I'm not going to be talking about much of the back end, except that we do that in Clojure, and our front end is built in Clojure. So we love functional programming here, and we also like open source. So check out some of our libraries if you haven't already. So what I'm going to talk about today is the power in simplifying your data flow through your system and having a predictability. There's a lot of interesting qualities in simplifying our data flow from our traditional approaches that we'll talk about. So this is like our kind of a top level view of what I'll be talking about. So let's kind of dive in. As an outline, first talk about ClojureScript, the UI data flow, and then some of the ways that we can manage our state data flow, which is they're related and they need to connect to each other, and we need to manage these things ideally in a simplified way. Okay, so why ClojureScript? Like I said, we use Clojure on the back end. So for people that use Clojure, using ClojureScript is sometimes a natural choice, but ClojureScript is also really good if you don't use Clojure on the back end. Some of the things that ClojureScript provides you specifically for the front end is this is a level of consistency and clarity that you don't normally get with JavaScript. I'm not going to sit here and rail off all the things about JavaScript that people find wonky. I'm sure you've seen talks like that before. But we have a level of consistency and clarity. And a lot of that comes from having immutability by default. And so what that means is all of ClojureScript's data structures are persistent data structures. And so you actually have to opt in to mutating data. And this becomes actually a pretty prevalent problem in JavaScript applications that I think people more or less start to deal with as kind of a second nature. And when you don't have to think about mutating things through your system, and you do it explicitly, your problems, you start to remove a little bit of complexity from them. So ClojureScript shares the same, mainly core library with Clojure. And this library has a lot of powerful abstractions over its data structures, whether these be vectors, lists, maps. And a lot of these abstractions are also extensible for your own data structures, which is actually really, really powerful if you use them tastefully. Macros, we have these in Clojure. They are magical, as people say. You shouldn't, not something you use on a day-to-day basis, but when you use them, they can incorporate some really powerful things. And particularly on the front end, macros aren't something that that a normal JavaScript developer has in their toolbox. we can do interesting things when we have a compile time transform to our code. And having, I think we'll talk a little bit more about some of the powers of macros a little bit later. And lastly, code sharing. We can share code between our front end and our back end. This is similar vein to Node, where you can have a Node runtime and use your templates on the front end. Except I think it's has a little bit different of a twist in that Clojure is on the JVM and ClojureScript's on JavaScript. So you have different host platforms, but the same code running across them. Again, touching back on that consistency thing in your programming model. So specifically, let's talk more about UI data flow. And I don't think that a talk would be complete without talking about MVC in this. I think it's a natural place to start. It's where a lot of our time and effort has gone for front-end development in the past couple of years. So with MVC and all of the different flavors around it, it's mainly concerned with separating different concerns of your application. You have different types of data. You have your presentation data. These are things like whether this button is checked or unchecked, whether it's menu showing, et cetera. And you have your domain data. And separating these things so that you can reuse your UIs and reuse your data is the main concern what we have here. The problem comes where this model is, it's not necessarily, it's a little bit too idealistic in terms of how these systems are actually implemented and how we grow these systems and scale them. Let's take a look at what an MVC system might look like. So this is just a generic kind of abstract system where we have some models, we have some controllers, and some views. And in this type of system, or a lot of these MVC structures, we have different relationships that kind of go back and forth between them. You've probably seen slides like this before, where you can create relationships kind of ad hoc, and they can kind of talk however they please. So there's different types of relationships. The controller mainly facilitates a lot of these. But you can also have relationships between models, directly to views. Views can sometimes talk to each other and so forth. And this, again, depends on the MVC flavor that you're using, but it is prevalent, and these types of relationships crop up in a lot of systems. And so what we end up with something like this in this type of system is we have state that's actually spread across all of these different parts. And not only is it just state that has to be managed in these individual parts, a lot of times it's shared state. And that can be hard to reason about. It can make our systems a bit more complex than we actually set out to solve. So we saw let's see. Yeah, let's actually look at what this means in practice. So if we have an MVC structure, let's add back our relationships, and we produce like an initial rendering of our application. We can apply some event handlers to our DOM, and then we'll get some user input sometime in the future. Those user inputs will usually come back in through the controller, and they'll kind of go wherever that view had configured them to go. And so this can be an arbitrary number of places, and the updating random bits and pieces, and a lot of times you can run into cascading effects. You get the idea that this can become a complex way to model a system. Looking at this thing from an outside view, zoomed out, it's kind of hard to understand all of the relationships that are there. You don't necessarily know the pieces of the architecture that are going to be modified by making some action on it. So this is actually a bit further away from this simplified model that we intended to use. So, of course, the functional alternative mindset, we have to question, what if we prioritized a simplified data flow? And what I mean by that is, what if the model of understanding our system was consistent? It didn't grow as we scaled out the features of our system, but it was a constant thing that we could easily reason about and build out. So ideally, we could have some sort of app state and then produce some rendering of that with a pure function. Producing some DOM rendering, initial rendering. Again, sometime in the future, we'll have some user events to close the feedback loop that'll produce a new app state. So when we produce a new app state, we can then rerun our pure rendering system, producing a new DOM output. This will probably look pretty familiar if you know about React. Another source of input that we have is network data. This can also trigger new app state, which would also in turn cause a new re-render. Oops, hit back. So what are we actually gaining by doing this? When we have a single direction data flow, what are the things that we are changing, and like what do we gain from that? Well, first, we're constraining the relationships that we can make in our system. Data can only flow in one direction. A child of this system can only take data that its parent gives it. And so what we do is we constrain ourselves to achieve a higher level of predictability. And when we have more predictable code, we can reduce complexity, we can write more higher quality software that we can reason about. And we've actually simplified the data model. As we add new features to this, the model of how the system renders doesn't actually change. And so we can be more productive in terms of moving faster, maintaining these systems and refactoring them, because we understand any downstream changes as well as upstream. Another interesting property of this is when you have a single value that you're rendering from, you can easily go in and look at whether an issue that you're trying to debug is a data issue versus a rendering issue. You can look at the entire app state that was rendered and see whether the data that you expect to be there is there. And if it is, then it has to be a display issue. Okay, so let's focus on this magical piece that allows us to do this pure rendering. And lo and behold, it's React. So React is a layer that sits in front of the DOM. It's a library by Facebook. It manipulates the DOM and handles events, and that's basically it. So what you do is you build a hierarchy of components where the data flows in a single direction. Each of these components has a render function, and the render function specifies, given the input data, what you would expect the output to be. So you're very declarative in that sense. And what you're actually doing is returning virtual DOM. And React, the reason why React uses virtual DOM is it allows you to be declarative. You give that virtual DOM what you would expect to be in the page to React. It looks at what's currently in the page, does a diff of that, and then pushes out a set of minimal DOM changes that need to be made to achieve what you expect to be on the page. So they're pushing all of the complexity of managing the state of the DOM into their library and letting you focus on building declarative components. This is pretty powerful. So specifically, what makes React good, a good match for ClojureScript? ClojureScript's been around for a while, much longer than React itself, at least publicly. And it seemed to kind of shoot off when we saw React come out. And there's some reasons for this. It's because there's some shared design principles. React and ClojureScript have an importance on functional purity and an importance on composition. And so what we mean by that is components can compose arbitrarily. Components have render functions that are intended to be pure. And there's a focus on simplicity through making the API predictable. So you can have any app state value and render that at any time, and you should expect to get a consistent output. Another important distinction from React with other front-end frameworks is that it has a focus on letting you use the functions and objects of your language. It doesn't introduce a bunch of new concepts. It doesn't like wrap your data in a bunch of scopes, for example. there's a pretty clear distinction that you're using the things, the concepts of the programming language that you're using to build it with. So there's a bit of simplicity there. And then lastly, React has a simple API. So it's a very single-purpose library, so it's easily composable from ClojureScript. So we have libraries like Ohm, Reagent, and Quiescent. At Prismatic, we use Ohm, and Ohm is an interface to React. You build your components through using ClojureScript protocols, and these are similar to interfaces in other languages. And Ohm also comes with a solution for managing your app state, and we use cursors for this. So just an example of what Ohm syntax might look like. We have some component that looks vaguely similar to the component on the front page of React. It's a hello message. It just has a render method that renders a div with the name that you give it in the data. So what we can do is create our app state, mount that component to some node, and then we can change our app state, and we would expect that the data on the page will render with the data that we give it. And so at Prismatic, we built a little library to help kind of abstract away some of the boilerplate of building Ohm components called Ohm tools to just make it a little bit shorter and a little bit easier to read. Definitely not necessary, but it helps. This is another one of those, the powers of having macros to make your code a little bit more concise. So let's also think about how we can simplify how state changes flow through our system. We've talked about React and how we render and passing our rendering data down. But state data flow. Like I said, with Ohm, we have cursors. So you start with a single application state when you mount your root component. And then every time you pull values out of that root component, you have a cursor to that piece of application state. And this allows you to pass cursors into components that they don't have to be concerned about the entire application state. They can be single focused on a type of data. They don't care where it came from. So you have reusable components in that sense. And you can use Ohm's API for transacting on cursors to modify the application state. And so we have an example here. It's just Ohm transact cursor f. And this is the form that it has. And f is just some pure function. So you can write your business logic in terms of pure functions, which helps keep everything easy to reason about. So just kind of a visualization. I know this might be kind of small for the people in the back. But if you have a larger application state, you can pull values out of it, reason about it locally. It behaves the same as regular maps and regular data in Clojure. And then you use the transact API to modify those values. So some of the properties, cursors are unadorned data, meaning that it's just, you use them just like you normally would other maps and vectors and so on and so forth. There's no notion of how you manage this data built into the library. And so you have this level of component modularity, and you also have an interesting aspect of efficiently knowing which parts of your application state have updated. Since the cursor, you're transacting on a certain piece of the app state, you already know whether or not it changed because you have an immutable value. It can only change if you have a new value coming out of it, as well as you know the path into the app state. So you know other components that use that as an input. So let's take an example of a Ohm cursor. Here we have a component for a comment in a comment thread. And some things to point out here is that this is a component that's, it doesn't necessarily know about its greater context of where it is in the thread or whatnot. And say we have some buttons on here to upvote or downvote. If we wanted to modify the state with this function called upvote, which is a pure function, we can transact upon this particular comment. Again, no knowledge of where we are in app state. And we can just use our cursor like normal data by getting out values at the bottom. So at the bottom, we pull out the text, the value at the text key. So this is pretty nice and declarative, right? So cursors, they turn out to be pretty well suited for deeply nested app states, just app states that have a tree structure in general, which is a lot of data. Once you start using just raw data structures to model your app state as opposed to putting everything in little bins, a lot of times it comes out looking very similar to a tree. However, relational data tends to be more normalized. You tend to put things in higher level in the application state and reference things from IDs. And I think this has interesting aspects to it. When you start doing this, you actually start needing more cursors in your components in order to make your transactions, to modify your state, to take you to the next thing from a single operation. And so you need to transact multiple times. I think this is an interesting aspect. And then the code, when you start doing this, starts to look a little bit imperative because you're doing transacts and order starts to matter. And it's reasonable to, when you get to this state, whether you think, whether your app state needs to be modified, it's something definitely very reasonable to ask yourself. But like I said, as you start to normalize your data and spreading it out, this type of thing starts becoming present everywhere. And to visualize this thing, this idea, let's say that we wanted to modify our component, our comment component, so that when we upvote something, maybe the thread that it's in wants to have some sort of running accumulation of the votes inside of it, and the article that this comment thread's attached to wants to know the last comment updated date or something. You have to pass these down. Not a huge deal because it's still declarative. It's still simple model. You can trace your data all the way through. However, the key distinction here is that we're not actually rendering any of this data that's in those things. So let's maybe think about how we can solve this problem. Well, first I'd like to actually kind of devolve this and do something that might be tempting to do, which is just kind of glob everything together and not actually pass those in as arguments and pass them in as a map. This can be tempting for programmers to kind of pass in maps of cursors. And this kind of is a dangerous road to go down because by looking at this component, you don't actually know what cursors it needs. You have to go and kind of trace through it. And so we're kind of losing a little bit of our value that we had before. And so maybe we can use some patterns, maybe borrow some patterns from other functional paradigms that we've seen before. And I think a common one that we've seen is when building games with functional languages. A lot of times we'll have the world, some representation of our world. We'll render it, and then we'll wait for some user input, process that input with the world to produce a new world. And then this whole process just reflows. And I think this has some interesting characteristics. It is obviously a gross oversimplification of the complexity behind doing all of these things. But from the model of how the program executes, it's very structured. And what this actually becomes is pretty related to is something that's been talked about recently, which is flux architecture that Facebook has talked about. And so this is an architecture. It's not necessarily a library or any sort of piece of software, but it's an idea for managing state. And the key parts of this is that you have a dispatcher, some stores, and some views. And the whole point of it is to have a single direction data flow between the pieces of the actions in your application, the semantic interaction points that users can take, and dispatching those into the stores. And the stores are concerned about managing their own data. And so the store will listen to message types, receive them or ignore them, and then update themselves accordingly. And then this whole system flows again. So this looks pretty similar to what we had before with our UI system. So I'm running out of time, and that we should move a little bit faster. ClojureScript with Flux, like how would you actually make this happen, and why? So the motivation is that you want to separate your views from the dependencies needed to do the actions that your views may that your views can actually operate on, and to generalize state management. This kind of concept isn't necessarily specific to Ohm. You could use it if you're using reagent or anything like that. And we want to leverage existing ClojureScript tools, specifically core async, because we're talking about asynchronously managing data, which is a perfect fit for what we're doing. So if we have a system, a hypothetical system, where we have this perform action, dispatch kind of layout, the UI will be concerned about performing semantic actions on the system. It's the action's purpose to produce messages that will be dispatched out to your models, and this happens asynchronously. So you can do some UI, or sorry, some I/O, do AJAX, get a response, and then dispatch some messages to your model. And in this case, we have models and not stores. And I think this is an important distinction, at least from our perspective, is that we can model our state with pure functions. We don't necessarily have to have stores that manage their own state, because we have the power of immutable values, and we have okay. So the first step is perform, and we have. So what would this actually look like from the component's point of view to do a system like this? And we have now come back to our very first component example, where we just take the component, the thing that we want to render. And then when you click the upvote button, you're just performing an action. This action is called upvote, and we give it some parameters called comment. Next in the chain is the action and the messages that it dispatches. So this is just an example action that we could have. And so the way that this one is set up is that actions return channels, core async channels, which if you're not familiar with core async, it's a library to take asynchronous data flows, asynchronous code and turn it into kind of sequential steps. And so what we can basically have the semantics of blocking in JavaScript, which we don't actually have. And we achieve this through macros. And so the purpose of this action is to return a channel that has messages on it. These messages get dispatched to our models. Another thing is that actions receive the current state of the application. This is just a snapshot of the current value. It's not some mutable reference or anything like that. So we can reason about the current state of the world, perform some actions in response. So we have next in the line is the model. And like I said, there's interesting ways of modeling state changes, specifically with pure functions. One way to do this is maybe you define a protocol for a model. Really the two important things here is that you want to have an initial value for your model and then some way to update the state of it. And so we have an init state function and then an update state. And so anyone that wants to be a model can just implement this protocol. And the purpose of the update state function is to, you are given your current value and some message. And you're expected to return either your state unchanged or your state modified from processing that message. this looks vaguely familiar to using a reduce function, right? So here's a really naive example of a comments model that responds to an add comment message. We have an initial state of just a map. It takes a message. We actually destructure it in the arguments to pull out a type of the message and the comment. We see if that type is add comment, and if it is, then we just add that to our current state. That works, and that's nice, but that's kind of gross. So we can build higher order abstractions on top of this. If we had a function called build model, we give it a map of message types to handler functions. We can now kind of see that we have something similar, but we have our pure functions to modify our state. Something that's nice about this is from building OM applications, you probably already have lots of functions that look like this that you apply during transactions. In addition to abstracting over this for individual models, we can build kind of higher level models. So this is an example of like a dispatch model that takes a map of other models. And so you can visualize this as a model that maintains a map of individual models that they manage their own domain. So we have a comments model, a threads model, articles model, and so on. And what that actually looks like on the other side is the comment state, the thread state, and the article state that those individual things manage. So these abstractions are pretty easy to build on top of protocols, and they compose pretty well. So we've gotten to here, and once you have the messages received at the models, and you give it a value of that current state, produce some new state, as you can expect, you can swap that value into your app state and render that thing again. And this whole system flows again. So this was just an example of how you can kind of rethink data flowing through the system for state changes. I think this has some pretty interesting aspects. It's pretty cool to experiment with this. I'm not necessarily saying it's a really great idea. You lose out on a little bit of some optimizations by OM where it knows where you transact on cursors since you're swapping in entire application states at once. Then again, if you are making multiple transactions to do a single state change, it might end up being faster. Just some things to think about. I think this idea is not anything that's really new. I think it's pretty cool to, it's pretty simple. It can be extended. We could actually potentially extend this to OM's ref cursors, which are a new feature, which basically allow you to have reference to a cursor in the app state without having it passed down to you. And so you might be able to regain some performance with that. And also, these things have a very strangely familiar syntax to transducers. So transducers are a new feature coming in Clojure 1.7 for defining transforms on collections or channels or anything. It's an abstraction away from the means of how those values are conveyed. And so we could actually hypothetically build something that uses transducers on the front end with this. And the cool thing is that although transducers aren't in Clojure yet, they are in ClojureScript. So just to wrap up, I know I talked about a lot of different random things. There's a lot of value in embracing immutability on the front end. It's not something that you have to try to do and to think about actively and to sorry, I lost my train. When you have immutability by default, it becomes much easier to reason about your programs, and it's important to invest in tools that prioritize simplicity and predictability for writing higher quality software. And when designing these systems, it's also important to constrain ourselves to the essential parts of what we're trying to solve. We want to avoid incidental complexity of putting ourselves in a system where we've actually created more problems than what we set out to solve. And that was basically all I had. Thanks.